What's going on, everyone? Patrick here, welcome back. And in this next video, what we're going to do is simplify these radical expressions, but we're also going to rationalize the denominator. So if there's any radicals in the denominator that's left, we have to get rid of those. So starting with number 1, we got the 6th root of 1 over 8. So when I get something like this, first thing I like to look for is, can I simplify the fraction within the radical? And notice 1 over 8, we can't simplify that any further. And so once I pass that test, what I like to do is then I like to take the radical and put it on the numerator and the denominator, like that. And the 6th root of 1 is just 1, right? The nth root of 1 is just 1. Any root of 1 is just 1. But what's the 6th root of 8 going to be? Notice we can simplify that. We can rewrite this as 8 to the power of 1 over 6. And then the 8 we can rewrite as 2 to the power of 3. And then 3 times 1 over 6 would give us 3 over 6, which would give us 1 over 2. 2 to the power of 1 over 2 is the same thing as the square root of 2. So this would end up being 1 over root 2, like that. But we can't leave it in this format. We have to rationalize the denominator. So what we would do, multiply the numerator and the denominator by root 2. So it's like we're taking this, multiplying it by 1. Right? And the reason why we do that is because root 2 times root 2 gives us 2, and then 1 times root 2 just gives us root 2. And notice that now we don't have any radicals in the denominator. So root 2 over 2 is the exact same thing as 1 over root 2 if you plug both of those into your calculator. And it makes sense because all we did was we took this and multiplied it by 1. Notice root 2 over root 2, that's just 1. So anything multiplied by 1 is just the exact same thing. Right? But because we didn't multiply it by 1, we multiplied by root 2 over root 2, it was just a different format, even though this and this end up being the exact same thing. Right? And notice there's no radicals in the denominator. Here there was a radical, so we had to rationalize it to get rid of the radical in the denominator. Right? Moving on to number 2, we got the square root of 3x over 5y. So first thing I look for, can I simplify this fraction? No, I can't. 3 over 5 doesn't simplify. X over y doesn't simplify. So then I distribute that radical to the numerator and the denominator. Can't simplify these separately, right? Square root of 3, square root of x, square root of 5, square root of y. And so what we want to do is get rid of this radical in the denominator. So what we would do is we'd multiply this whole thing by root 5y over root 5y, like that. So again, it's like we're taking this, multiplying it by 1. And what's going to happen? Well, we'd end up with root 3x times root 5y over root 5y times root 5y just gives us 5y. And then because these are the same roots, we can multiply these expressions. So 3 times 5 gives us 15, and then x times y just gives us xy. And this would be over 5y. Okay, so this and this, they're the exact same thing. It's just now there's no radical in the denominator. We rationalized it. So we got root 15xy over 5y. Both of them are the exact same thing. Moving on to number 3. This one's a little unique. So we got the square root of x to the negative 2 minus y to the negative 1. Now when I get something like this and I got these negative exponents, I like to change them to positive exponents. Like that. Right? Just looks nicer. And notice with these two, what was happening was we were checking if we can first simplify the fraction, but notice we had one fraction for both of them. But here, we don't have this in terms of one fraction, it's two fractions that are subtracting. So what we want to do here is we actually want to combine both of these into one fraction. So what I'm going to do is I'm actually going to take, let's forget about the radical sign for now. Let's just take this expression, combine it into one fraction. And since you're subtracting, you need a what? Common denominator. So you would multiply these two to get a common denominator by the respective terms. And what we multiply at the bottom, we've got to multiply at the top. Here, multiply at the top. So x squared y would be the common denominator. Then 1 times y is y, 1 times x squared is x squared. Okay, so this and that are the exact same thing. It's just now this, notice, it's one fraction. So we can rewrite this now as the square root of y minus x squared over x squared y, like that. Notice this doesn't simplify, so what we would do, exact same process, we would put the numerator under the radical, put the denominator under the radical. Now, from this point here, there's actually multiple ways we can go about this. We can rationalize at this point if you want, like that, to get rid of this radical. But what I actually suggest before rationalizing is checking whether you can simplify these radicals here. Now this you can't simplify, this radical, this root y minus x squared, but this you can, because notice that the square root, let me erase this for now, of x squared y, that's the square root of x squared, the square root of y. What's the square root of x squared? That's just x. And then we have root y. And so this simplifies to x root y. So this and this are the exact same thing. And what we can do now is just get rid of the root y. We don't have to multiply by that large expression. We can go about it that way, but then what's going to happen, I'll show you too actually, after I simplify this, if we go about it the other way. What's going to happen if you multiply, if you rationalize this at this point, there's going to be a lot of simplifying to do later on. Versus here, there's not going to be any more simplifying to do. So what would happen is, when we rationalize this, we would end up with the square root of y minus x squared times the square root of y. This is going to be all over x. Square root of y times the square root of y is just y. And then these two radicals we can multiply. And so we'd end up with the square root. This, and we're multiplying by this whole thing. So that's in brackets. So I'm going to put the y in front there. That's going to be all over xy, like that. So that's the actual final answer right there. And this could actually be in a different format too, I just realized. So you got to be careful if this is like a multiple choice test. You might get this solution, but you also, they may distribute the y. And that might be a solution as well. Both of them are the exact same thing, right? It's just this y was distributed, right? But my preferred format is this over here. So that's the final solution. Now let me show you what would happen if you went about rationalizing from here. Let's see if we can get this exact same solution. What would happen is, you wouldn't simplify here, but again, you'd have to simplify later, which would be a little annoying. I find whenever you get a chance to simplify, the earlier the better versus later, because then things get more complex. So here, notice these two would multiply to x squared y, and then we can multiply both of these, so we'd have x squared y times y minus x squared, all under the root. Okay, but now from here, what would happen is you'd have to recognize that this x squared you could take out, so you can rewrite all of this as the square root of x squared, square root of y minus x squared, all over x squared y. And then notice the square root of x squared, that would just give us x, and then one of these x's and one of those x's would cancel out. And so we'd be left with this, and then we can recombine those. Or you didn't even have to split them up if you don't want to. You could just take out the x squared. What I'm saying is just, you got to take out the x squared now, make it an x, and then cancel out with the x at the bottom. Right? So it's just, the simplifying is just more steps to get that exact same solution. I feel like it's easier to simplify here before rationalizing, and then the rationalizing is easier because you only have to multiply by root y over root y. Okay, but whichever way you want to go about it, you can do that. I'm just showing you the way I would do it. So moving on to number 4. Number 4 is actually going to be similar to number 3. We can rewrite this as 3 over x squared plus 2 over y to the 3. Like that. All right, this and that, exact same thing. Two fractions, you want to combine them into one fraction. So common denominator, multiply this by y to the 3, multiply this by y to the 3, multiply this by x squared, multiply this by x squared. So we'd end up with 3y to the 3 plus 2x squared all over x squared y to the 3, like that. And now, because we have this in terms of one fraction, we can put the radical in the numerator, put the radical in the denominator. Then same thing here, you're going to want to simplify here. But the point is that when you get something like this, here, here, it's also going to be here. There's going to be two expressions. You want to put them as one fraction so you can take that radical, put it in the numerator, put it in the denominator. So just in general, when you got that, that's the same as this. Right? It's one fraction. But if you have something like this, two fractions added, that doesn't equal the numerators added and the denominators added, right? This is not a property. This is a property. So you got to make sure you have one fraction when you're doing these kinds of questions. Here in number 5, it's already one fraction, so it's going to be easier. But for example, here we're going to have to make everything under the radical in terms of one fraction and then apply that property. Okay, so from here, again, if you want, you can rationalize this, but I would simplify that first. I would simplify that denominator. This ends up being the square root of x squared, square root of y to the 3. The square root of x squared is just x. This we can rewrite as y to the 3 to the power of a half. And same thing, there's like a 2 there, so we want to split up that y to the 3, where one of the y's, the exponent, is a multiple of 2. What's the highest multiple of 2 that's less than or equal to 3? 2, right? 2, 4, 6. 4 is greater than 3, so it wouldn't work. So this we would split up into y to the 2 times y to the 1. Like that. 2 times 1 over 2 is 1. Y to the 1 is just y. 1 times 1/2 is 1/2. Y to the 1/2 is the square root of y. So this denominator simplifies to that. And now that's going to be way easier to rationalize, because we only have to get rid of the root y. Okay, so we would just have to multiply this by root y over root y, and we'd end up with root this times this expression all over x, y. Root y times root y is y, and then y times y is y squared. So we would end up with a y squared at the bottom, like that. And you can't simplify that any further. Again, another format, you might see this, you might see the numerator distributed, so that would be 3y to the 4 plus 2x squared y. So either one of these formats can maybe come up on a multiple choice test. Right? So that's the final answer for number 4. I'll put this format. Now moving on to number 5. Number 5 is actually kind of easy because it's already one fraction, as I mentioned. So it's just the square root of x plus 3 times the square root of x minus 3. Again, what you want to check, I forgot to mention, can you simplify this fraction? No, you can't simplify this fraction. X plus 3 over x minus 3, you can't simplify. So from here, split up the radical, and then rationalize the denominator. Check if you can simplify that denominator. You can't simplify the square root of x minus 3. So we could rationalize from here, and we'd end up with the square root of x plus 3 times the square root of x minus 3 all over this times that is just x minus 3. And then you can combine these two. Like that. And then this is a difference of squares, right? So if you like FOIL it out, you'd end up with the square root of x squared minus 9 over x minus 3. So that's another format. You could see it. You may actually see that, because I feel like maybe even this is nicer than having the x plus 3 times the x minus 3. Right? Rewriting it as x squared minus 9, the square root of x squared minus 9 in the numerator. So this here ends up being the square root of x squared minus 9 over x minus 3. However, again, you may see this format come up. Both of them are the exact same thing. The point is, there's no radical in the denominator. And then finally, number 6. This one's going to be a little hectic, but not too bad. So 1 over 4a, here, got to combine these into one fraction. So I'm going to rewrite the x squared as x squared over 1 minus 3x over y. Common denominator between 1 and y is y. So we'd multiply this by y, multiply this by y. Got the 1 over 4a, x squared y minus 3x over y. Right, this ended up being x squared y minus 3x, and then the common denominator is y. It's all now one fraction. So we can distribute the radical to the numerator and the denominator. Can you simplify square root of y? No, you can't. But we want to get rid of it. Multiply by root y over root y. And so we would end up with, we can combine both of these radicals. All over 4ay. This square root of y times square root of y is just y, so we'd end up with a y, like that. Okay, another format, actually I just realized this could be in. So another way this could be written is, if you notice, from this we can actually take out an x. So we could rewrite this as xy times xy minus 3. Right? We could take out an x, factor out an x from both of these terms into the front, and this would be all over 4ay. Okay, so I know it's kind of annoying going through these different formats and might be a little intimidating, but I'd rather you get exposed to this now versus later. So that is one format, and then another format is where it's all distributed. So this would be x squared y squared minus 3xy over 4ay. Like that. Basically, all of these are the exact same thing. We could have got here too by just distributing the y to the bracket. So you got to be careful again on a multiple choice test. Any of these can come up. So even though you're getting tested on rationalizing the denominator, which we did, notice there's no radicals left in the denominator, you got to be careful with certain simplification that can come up in between.